Greetings, fellow mathematicians. We're going to be taking a look at another really good trigonometric substitution problem that comes down to another tricky trig integral. So let's start by choosing our substitution. And if we take a look at the square root, we have the square root of x squared plus a number. Make sure you're comfortable realizing the order of addition could be reversed. So here, this looks like a number squared plus x squared. We're going to be using a tangent substitution. And since the number is 1, we're going to be using a as 1, so we're going to make a basic substitution. X equals just tangent theta. All right, we're going to want to calculate the differential dx. The derivative of tangent is secant squared theta. And let's go ahead and take our substitution and get the square root to cancel. So the square root of x squared plus 1. We're going to plug in our substitution, x as tangent theta. So we get the square root of tangent squared theta plus 1. And we can immediately use the second basic Pythagorean identity, which if you're not comfortable or aware of that, definitely go ahead and take a look at the video I have linked down in the description, where we go through everything you need to know about trig substitution. Here, we're going to be using a Pythagorean identity. Tangent squared theta plus 1 equals secant squared theta. So we get the square root of secant squared theta, and the square root now cancel, leaving you with just secant of theta. All right, we're just going to go ahead and plug all this in, and the part that's usually overlooked or forgotten by students in a Calculus 2 course is forgetting to substitute the x squared in the denominator as well. Replace all x's with your substitution. For this problem, x is being replaced with tangent theta. So let's immediately do that. We get the integral of 1. X is being replaced with tangent theta, so we get tangent squared theta in the denominator. The square root, we just simplified that, and we saw that that reduces down to just secant of theta. And as always, like we've mentioned in previous trig substitution problems, don't forget to convert the differential dx in terms of theta as well, which comes out to secant squared theta d theta. All right, and from here we can simplify this. We can have a factor of secant cancel out, and what we're left with is the integral. We'll move that secant theta into the numerator. We get the integral of secant theta divided by tangent squared theta. And at this point, we now have our trig integral. Now, this doesn't seem to fit any of those two standard types of trig integrals in terms of powers of sines and cosines or powers of secants and tangents. A great tip and technique to use for these weird trig integrals: rewrite everything in terms of sines and cosines. And here, we can probably use a basic substitution after that. So let's go ahead and take secant theta divided by tangent squared theta and rewrite it entirely in terms of sines and cosines. All right, so we have secant of theta divided by tangent squared theta. Let's use some basic trig identities. Secant is 1 over cosine. So we get a fraction in the numerator, 1 over cosine of theta. Tangent squared, that should convert and be rewritten as sine squared divided by cosine squared. And now we just use some fundamentals. Since we are dividing by a fraction, it's going to be equivalent for us to multiply by the reciprocal. So we're going to keep the numerator the same, 1 over cosine of theta. But now we're going to multiply by the reciprocal. We're going to flip what we're dividing by. We're going to be multiplying now by cosine squared divided by sine squared. And that's nice because now we can get a factor of cosine to cancel. And we're left with cosine of theta divided by sine squared of theta. And that, unlike our original trig integral, which doesn't seem to have an obvious u substitution, here we can use a u substitution, u as sine theta. Since the cosine theta in the numerator, we can use that for the differential, du. All right, so let's just go ahead and rewrite that. We rewrote this trig integral entirely in terms of sines and cosines. Cosine theta divided by sine squared theta. And now we can use our substitution, u equals sine theta. All right, du is going to be then cosine theta d theta. And this will convert to a very simple integral. Cosine theta d theta just becomes du. And then 1 over sine squared, we're going to convert that to 1 over u squared. So it looks like as our integral, I'm going to rewrite the 1 over u squared as a power, u to the negative 2. And that should be very easy to integrate with the power rule. So go ahead and add 1. You'll get u to the negative 1. Divide by the new power. There's your antiderivative. And now we just need to work backwards through our various substitutions. Let me first rewrite that as negative 1 over u. And first we're going to replace u back as sine of theta. So we get negative 1 over sine of theta. All right, at this point, we now have our antiderivative in terms of trig functions of theta. We're going to convert back trig functions of theta to x, as always, using our conversion triangle. So let's go to our substitution to go ahead and make that. If you don't feel comfortable about where the conversion triangles come from, again, go through the video I have linked down in the description where we go through that and take our time. So let's go to our substitution. We have it here as x equals tangent of theta. We're going to rely on basic SOHCAHTOA. I'm going to flip the sides and write x over a denominator of 1. So let's rewrite this as tangent of theta equals x over 1. And we're going to think of tangent of an angle as opposite over adjacent. And we can label 2 out of the 3 sides in our conversion triangle. All right, and if we go ahead and label them relative to our angle theta, the opposite side will be of length x. But now it's the adjacent, not the hypotenuse, that is of length 1. Work out the hypotenuse using the Pythagorean theorem, and you'll get that comes out to the square root of x squared plus 1. And again, not a coincidence that you get the original square root or radical expression in your integral. All right, now what we want to convert is sine of theta, and notice where it occurs in the denominator, and that's okay. We're going to replace sine of theta with a fraction, and since we have 1 over that, we're just going to reciprocate or flip that again. So let's go ahead and use our conversion triangle to determine sine of theta. And again, if we rely on basic SOHCAHTOA, sine of an angle is going to be the opposite side, x, divided by the hypotenuse, which is the square root expression. And now we just need to recognize that sine of theta, we have it here as 1 over sine theta in the denominator. So we're going to go ahead and flip that, and we get our antiderivative. We have a negative. And just be careful to flip that. You get now the square root of x squared plus 1 over x. And plus c. And we get our antiderivative. And this is a fairly standard Calc 2 problem. Not a whole lot of work. And the trig integral here, it's actually fairly straightforward since it comes down to really a basic u substitution. If you're comfortable rewriting it from your original trig integral entirely in terms of sines and cosines. And again, that is a great tip or technique whenever you encounter a trig integral. All right, hope you enjoyed this problem. I hope you're learning a lot. If you are, support the channel, like and subscribe.